Hello everyone, I'm Priya Hassan. I'm from India and I teach at the Maulana Azad National Urdu University. This is situated in Hyderabad in India. And I'll be talking to you today about research projects with Gaia. And yeah, so our picture, like we know about the transient universe, another very important thing which we are now very well aware about is the dynamic universe. So in principle, we know that when you even look at a galaxy image or you're looking at a star, it's definitely in motion, right? But the period at which you are watching it is such that you do not perceive the motion, though the motion can be perceived at a larger time scale, right? So it is a dance which you're just seeing snapshots of. So, when we actually studying stars, how has the growth of knowledge been of us about stars? So, the essential earlier picture was where we had a 2D picture, you had positions, star counts, and then it built up to us having 3D picture where you study the parallax for the nearby stars, through which you'd actually estimate their distances. And then gradually, as people progressed with photographic plates, etc., people could actually measure, astronomers could actually measure proper motions and the transverse velocities of stars. And then with the advent of spectroscopy, you actually could measure radial velocity, chemistry of stars. And now for stars, we have more than about 12 parameters, astrophysical parameters, which can describe the stars based on all this data, which involves its ages, its histories, its multiplicity, and various other factors because of the kind of information that is now available to us about these objects. Right? So now, how has our growth been in the terms of astrometry? You can see the picture is here, the Big Dipper, and you can see that these individual stars, they actually have a motion. If you look at the counter over here, you can see, I'll just go back and show that to you. You can see the counter as you're moving with thousands of years. You can then perceive the motion of the stars, which is actually a very small amount per year. And therefore, precise motions of these stars is what is called astrometry. And in principle, it was possible only for close by stars. But so if you actually look at the way astrometry has developed, you earlier had Tycho Brahe, who with naked eye observations could get to a precision of about 50 arc seconds. Then you have an improvement in it. And then you have a big steep fall over here comes when you have space astronomy, where you have the Hipparchus mission coming in over here. And at that time, you already have a precision of about 0.1 to with the Tycho, you have the Tycho catalog, you have 0.01. And then we had the advent of Gaia. And Gaia actually, you see such a steep, drop or the improvement rather in astrometry, where you are going at the micro arc second level in your precision for astrometry. So Gaia actually promises us that kind of astrometry for a billion stars of our galaxy. So there have been various astrometric catalogs. I won't go into details, but you can gradually see how the precision of these catalogs has improved over time. Now, now this kind of precision is only possible with space astrometry because that's when you actually have a stable sky and you can actually do it with this thing. It's also with an all sky coverage and this thing. So the Hipparchus mission was in the 1990s, and you had about 1 million stars which were observed with it with very high precision, and then with which you could ever measure stellar motions. I'll just rush through this. You have transverse velocities, which is measured in terms of proper motions and RA and in DEC. And then you have the radial velocities and use that to find out the space velocities. Now, so that's how you actually, I won't go into it. So Gaia actually is the one which actually got a big revolution in the study of stars, typically of stars in our galaxy, as well as a whole lot of celestial objects, ranging from quasars and even solar system objects. And basically, the advantage is that because once you're out in space, then you do not have the effects of the atmosphere, you have much more stability. And therefore, you can look at this, you have two mirrors which are at an angle of 106 degrees, and therefore you can actually do what is absolute astrometry with the Gaia mission and its focal plane, etc. I won't go into these details. So essentially, what does Gaia do? Gaia gives you excellent accuracy in astrometry, basically in terms of 6 coordinates. So you have your RA, your DEC, you have parallax, which gives you distance, you have proper motion in RA, proper motion in DEC, and you have radial velocities. Right now, so what happens with this is that the idea is One can study the neighborhood of the sun with very high precision, and then as you improve your emissions, the data releases, you can get even larger. So, what are the kind of jobs you can do with that? So, for example, the latest mission, which is the focus mission, which is the data release of Gaia, that is very good even for solar system objects. So, you can actually use it to study the vicinity of the sun. You can actually very well study even the whole structure of the galaxy, because you can it give with that with a milliarc second kind of precision, you can go up to a distance of the size of the galaxy and actually study all the components of the galaxy. Now, I do not have the time to go into details, but that's what's actually happened, that with Gaia being added in, there's a lot more we have understood or learned about our galaxy in terms of its structure and this thing. So what happens with all this data? You can, like I said, you'll get all the distance velocity distributions for all the stellar population of the galaxy, the disk, the halo, and that has actually helped us to build up what is called galactic archaeology, which is a formation history of the galaxy itself, right? As well as you are also looking at the neighborhood of the galaxy, the LMC, the SMC, supernova base, as well as quasars, for example. So that is also contributes into the celestial reference frame and the measurement of various parameters of that kind. Exoplanets are also something which is going to come out very well from Gaia, but not the present data releases, the future data releases. But at present, what we can do is we can characterize the host stars of exoplanets very well using Gaia data. But once we later on have data from the future missions, we will then have much more accurate light curves, etc., with which we can actually work on exoplanet discoveries. And then solar system objects, which are in the neighborhood, not very bright, they can be also very accurately measured, because this is an all sky survey. So, in principle, Gaia observes the same star about 70 different times, right? It's going to be observed by Gaia. The spectroscopy in Gaia, I mentioned to you the radial velocity aspect, but the radial velocity is obviously limited to the magnitude of the stars. So, it's typically at present 12th magnitude, 14th magnitude. That's about the brightness limit we'd have with the spectroscopy with Gaia. So there have been various data releases of Gaia. So I'm jumping straight to the second data release, where you have, this was the amount of objects for which you have position and brightness. You have parallax for 1.3 million. This is 1.6 or 1.7 million positions. And then what you also have is you have photometry. There's color. So there are two filters. There's a red filter and a blue filter. And with that, we also have color information about these stars. The early data release was out. I won't go into those details also. And what was actually done is that stars within 100 parsec of our sun could be very well studied. There, you can have a look at these various sources which are there on the net, which actually gives you a lot of data about the stars within the neighborhood of the sun and the kind of, so there's the Gaia catalog of nearby stars. Also, very good studies were made using Cepheids, or relay as standard candles, and basically, yeah. So, distances to globular clusters, for example, this is using Gaia DR2 data, EDR3, that is the early data release 3 data. And we have already an improvement in a factor of about 2 in proper motion, parallax, etc. And therefore, the sample of globular clusters, which has been studied with EDR3, is far more than what was DR2. Also, for globular clusters, people have been studying dark matter halos using the precise astrometry of these things. So what they basically do is you study the velocity dispersion in the outskirts of a cluster, and then that can actually be correlated to what is compared to what is expected from Newtonian dynamics. And this comparison can actually give you a very good estimate of the dark matter in globular clusters. Another very important contribution of Gaia has been in the study of the HR diagram. Now, the HR diagram is the holy grail for all stellar astronomers, and therefore, but what happens is that for this you need absolute luminosity and color, and for the absolute luminosity you need very precise measurements of distances, and that's exactly what Gaia gives you, and therefore we have very accurate HR diagrams. And what was found with the Gaia HR diagram is very well we could map the white dwarfs, which was not very well mapped earlier, but in this case it's very well done with this thing. You can actually see it. I won't go into these details because most of these movies, the links I have provided in the presentation. So you can have a look at these videos where you can actually see how these studies have been made of various objects. The HR diagram also, this thing. A very good important study which was also made with Gaia was about the acceleration of the sun. Like I told you, because you can look at distant objects, for example, quasars. So what they basically did in this study is that you had the apparent motion of distant quasars, which would get reflected, which is in the motion of the sun, and rather the motion of the sun can be compared to that, which give you the reference frame, and therefore in this one could actually find out the direction in which the sun is accelerated, as well as aspects like that. So this one is the data release 3, which is the most recent data release, which was out last year, in last June. Studies even of the galactic anti-center, which were earlier not very well possible, are there with Gaia data. And that's the data release 3. So now I'll focus about what I've been working on. So I basically work on open clusters, which are groups of stars which form from the same molecular cloud. And therefore, since they form from the same molecular cloud, the velocities as well as distances have to be close related. And in that way, one can actually, and these are ideal objects with which you can study the HR diagram and various things about stellar evolution as well as formation. So one of the major, most important problems in finding a cluster is, like, if you have a piece of sky like this, is actually finding out which of the stars actually belong to this cluster, right? And typically something very simple can be done with a virtual observatory tool, which is TopCat. For example, over here, I can show you that for a certain cluster, if you actually make a plot of proper motion deck versus proper motion RA, you can see that the field stars would be centered somewhere around 0, 0. But the cluster stars would be centered around another region, and that can be actually used to identify members of the cluster. And if I further plot it here in an array deck plot, what you see on the left, you can see that all the members seem to be moving in the same direction. So that indicates that we have actually identified members of an open cluster very well using Gaia data, because you have, and this is just with the velocity cut. If you make another cut in terms of parallax, you can then again look for stars which are moving with same velocities as well as at the same distance, right? So therefore, there's a very big issue about membership and how membership can be determined using Gaia data. And that's what we've been working on with a lot of this thing. And the thing is that because Gaia is giving you, for a certain region of the star of the sky, thousands of stars, right? And you want to find out which of these stars belong to that open cluster, right? So what we did is we tried using machine learning tools, since there's a lot of mention about machine learning and big data over here. So that's one of our first papers where we actually tried to study the membership of stars using a method which is called random forest. Now, random forest is a supervised method where you actually use a training sample with which you can actually find out the members. Now, there's lots of details about this will be done tomorrow with the talk by Hassan, where he's basically going to talk about these methods and what we did. But essentially, this was using supervised techniques. And then we also use this very well to actually look for kinematics in a very young star forming region, which is serpents. And what we basically did is we used catalogs from different wavelengths, for example, infrared, X-ray wavelengths, to identify young stellar objects, the YSOs. We matched them to Gaia data. And then we actually used, again, machine learning. We used methods called DB scan, optics, and HDB scan. These are 3 different methods. You'll be hearing more about it tomorrow. And basically what we did is that we essentially had a very small sample of stars which matched barely 86 stars. But then when we used machine learning techniques, we got about 1,000 stars for which which were Gaia, which were matched with Gaia, with which we could very well study the kinematics of these stars. Now, such things can be very well matched with, for example, 2MAS and WISE data to classify the YSOs, so that we could actually look at how has star formation progressed in this region, in the sense what is the different classes of YSOs we have in different parts of this star forming region, right? As well as the kinematics, because that we have it from Gaia. We also tried to continue with this work using unsupervised methods. So those were basically using clustering techniques in machine learning. So there was one which was with BB scan, and there's another work which we are doing, which is very soon we'll be submitting it, which is using Gaussian mixture models, again, to identify members. So I think that, especially for the open cluster community, that is one of the biggest contributions of Gaia in terms of membership. And the talk after me is also about that. So I look forward to hearing more about it. Some of the other work I tried out with Gaia is, for example, what's interesting is the HR diagram itself has structure. Okay, it has structure. Like, for example, there are some clusters which you can look at over here, 9 of them which I've showed, but there are actually gaps in the main sequence. Right now, that's something very interesting, because for some reason you don't have stars. For example, in this region, either these stars have moved up or down. Most probably that's what's happened to them, and therefore they've been brighter or they've got redder. And for some reason, there's a gap over here. And the important thing is, these are very important indicators to stellar evolution, right? Why should you have gaps like this? And therefore, what we did is we used a very, rather quite an old technique, which is a chi-square technique, to actually identify gaps in these 9 clusters for which gaps were reported, to actually actually see the significance of these gaps, whether their significance, and how can they be matched. What are the spectral types? You can see the spectral types of the stars at which we have the gaps. And this paper has already been accepted. It should be out soon. Yeah. Another work which we did, which is an interesting work, is also looking for the binary fraction in stellar clusters. So we took all the clusters which were within 1 kpc of the sun. There are about 376 clusters. We used this software called Azteca to actually get the binary fraction. And what was interesting is we found that the binary fraction is constant. It's about 0.29 for all these clusters, irrespective of their size, age, and mass. Right? All the other interesting stuff can be done is we're studying various, moving groups and clusters also, because you have the kinematic data. And since I've got to finish, I would also like to guide you towards this paper of mine, which is called Gaia, the 3D Milky Way Mapper. This is a semi, it's not a very technical article. It is more at an educational level to actually guide people as a good starter to Gaia data. Yeah, so thanks a lot. Thank you.